Okay. Okay, so our next speaker is Yizhi You from Princeton University, talking about Fracton, critical point, and topological phase transitions beyond renormalization.
Hey, thanks, Lucas, for the introduction. Also, thank the organizer for organizing this 3-week program. Today, I will talk about Fracton critical point and a new type of topological phase transition that is beyond the renormalization perspective. Because our focus today is about phase transitions. So in my first slide, let's have a 1-minute overview about the historic development for critical phenomenon and the phase transitions. So there are 2 milestones which help us to understand the critical phenomenon and phase transition. The first milestone is known as the Ginzburg-Landau theory for phase transitions. And it emphasized that for a phase transition which connect 2 phases with distinct symmetry patterns, we can write down the phase transition theory in terms of a fluctuation of the order parameter, and the order parameter usually correspond to a local operator like a spin polarization, a boson operator, or orbital, a valence bond orbital operator. And the phase transition between a disordered phase toward an ordered phase can be written in terms of the fluctuation of the order parameter, which finally condensate, and the order parameter condensate breaks a certain type of symmetry. So that describes the spontaneous symmetry breaking between a disordered phase and symmetry broken phase. And second, the second milestone for critical phenomenon is if we focus on the quantum or classical critical point, the correlation function has a power law decay, and that implies the correlation length is divergent at a critical region. And hence, we have to visualize everything at a larger spatial scale. So there, K.G. Wilson developed a renormalization group theory for phase transition and critical point, which emphasized that at a quantum critical point, we can do some renormalization, or say coarse grain, such that we coarse grain out the local fluctuation, which came from short wavelength physics, and only keep the long wavelength mode as our essential description of the critical phenomenon. And because of the renormalization, people figure out that a quantum critical point, if we look into the correlation function or the operator scaling dimension, the critical exponent of these operators shows a certain universality, which is usually independent of the microscopic form of the Hamiltonian, but only dependable to the space-time dimension, to the symmetry, to the locality of the system. And today, I will talk about a new type of quantum critical point that is beyond such historic paradigm. So the historic paradigm emphasizes that most phase transitions correspond to the Landau type phase transition, where everything can be written in terms of a fluctuating local parameter, and parameter condensate give rise to the phase transition. However, during the past few decades, because of the development which engender a zoology of new quantum phases for the topological phases or symmetry protected topological phases, people find that in principle, 2 phases with the same symmetry patterns can also be connected by a quantum critical point or continue phase transitions. And albeit the fact that the 2 phases between a quantum critical point have the same symmetry pattern and cannot be distinguished by any local order parameter, it turns out that these 2 phases have different intrinsic entangled patterns, so they belong to different topological sectors, and we can use some topological invariant or say many-body invariant to characterize 2 phases. So there, it was extensively studied that there can exist a large number of topological phase transition, which is a critical point to connect 2 phases with same symmetry pattern, but distinct topological characters. This includes the quantum Hall or fractional quantum Hall plateau transitions, or the 1D Hall-Dann chain, which is a topological paramagnetic chain toward a trivial quantum spin chain transition. And second, historically, the understanding about critical phenomenon was mainly engendered by the renormalization group picture. And the essence of renormalization group lies in the fact that the long wavelength physics become very important at a critical point, and it is the long wavelength physics or long wavelength method which control the quantum critical point. However, today we will encounter with an example such that at a quantum critical point, such kind of theory is beyond the usual understanding of renormalization. And in particular, at a quantum critical point, it turns out that the short wavelength physics or short wavelength mode can be very important, and it will even control the quantum critical behavior. To begin with, let's first have an overview of some common topological phase transition in 1D quantum spin chains. So for topological phase transition, it is different from the usual Ginzburg-Landau theory for phase transition in the sense that it cannot be written in terms of a fluctuating local order parameter. And for local order parameter, it can change continuously when you proximate to the quantum critical point. However, for topological phase transitions, different phases are different by a topological invariant, which are usually chosen to be a discrete value, or they have to be discrete under a certain symmetry constraint. And because of that, this raised two questions we want to address here. So first, if there exists a topological phase transition, connect two phases with different topological pattern, what happens to the topological index or topological invariant at a quantum critical point? And how does the topological order or symmetry protected topological order disappear when you proximate to the critical point? And second, if we begin with a topological order or symmetry protected topological pattern and then drive it into a trivial phase, what happened to the topological information? Does the topological feature in the SPT phase or topological phase also affect the quantum critical point? In particular, does the topological term change the universality of such kind of phase transition? Okay, so now let's have a 10-minute overview of a well-known example for 1D topological phase transition. So the topological phase, actually, it's a symmetry protected topological chain we will begin with. It's known as the Haldane chain, where in 1D we have a unit cell which contains two spin 1/2 degree of freedom on the same side. And the Haldane chain can be written in terms of a Troy wave function such that every two spin between the site, between the unit cell, has an antiferromagnetic interaction and finally project two spins between the side into an SU2 singlet. So the ground state wave function is a bunch of singlet between the site, and bulk degree of freedom is fully gapped. However, once we encounter with a boundary, the boundary would carry a free spin 1/2 degree of freedom, which is not paired with any of the partner in the bulk. So at the boundary, such kind of topological paramagnetic chain carries a free spin 1/2 degree of freedom. And in the presence of time reversal symmetry, there should be a twofold robust degeneracy at a boundary. This is known as the spin on zero mode at a boundary. And the understanding of the Haldane chain was developed by the topological nonlinear sigma model with an O3 theta term. And in the Haldane chain, theta would flow to a stable fixed point where theta is equal to 2 pi. And because we're talking about a topological phase transition, so we have to think about a Hamiltonian which has competing order. So we still begin with this spin chain where each unit cell have two spin 1/2 degree of freedom. And the Hamiltonian contains two competing terms. The first term is the antiferromagnetic interaction between the two sites between the unit cell, which has a tendency to generate a SU2 singlet between the bond. And this is what we know as the ground state of the Haldane chain with a free spin 1/2 H0 mode. And it can be written in terms of a topological nonlinear sigma model with an O3 theta term where theta equals 2 pi. And the second term is actually an antiferromagnetic interaction between the two spin living inside the same unit cell. And when J is large, we are in the Haldane chain limit. If J is very small, then the on-site interaction finally pair the two spin into a spin zero mode. So this is equivalent to a spin zero chain, which has no entanglement between the site. And this is a trivial spin chain, which does not have a topological theta term, or we can denote it as theta equals 0. If we tune this parameter in J, there is a critical point at J equal 1, which connect the trivial chain and the Haldane chain, or connect the region where theta equals 0 versus theta equals 2 pi. And what happened at a quantum critical point? So a pictorial way to understand the quantum critical point can be characterized by something like a percolation picture. Because at j equal 1, the spin interaction between the unit cell versus the spin interaction within the unit cell are also almost of the same strength. So these two type of patterns, the Haldane chain patterns and the trivial chain patterns, do compete and coexist in the bulk. And once they coexist, there could be a typical defect, which is a domain wall defect that separates the region with a Haldane chain pattern where theta equals 2 pi versus the trivial chain pattern where theta equals 0. And this domain wall defect is nothing but something like the Haldane chain H, which contains a free spin 1/2 degree of freedom in the bulk. So at a free transition point, because two distinct patterns percolate into the bulk, at a domain wall, this domain wall behaves like an H mode between the Haldane chain versus trivial chain, which contains a free spin 1/2 degree of freedom. So at a quantum critical point, the previous H modes, which is localized in the Haldane chain, now entered and dissolved into the bulk. And at a quantum critical point, because different patterns fluctuate and resonant to each other. So once the domain wall position strongly fluctuate along the 1D chain, the position of this spin 1/2 mode also strongly fluctuate. So the spinor actually hope when the domain wall pattern fluctuates. And from the field theory side, because the Haldane chain is characterized by a 2 pi theta term, while trivial chain does not have any theta term. At a boundary between two distinct regions, there is a free spin 1/2 degree of freedom, which is characterized by a zero-dimensional O3 level 1 Weizmann-Witten term, which exactly represent a spin 1/2 degree of freedom in a path integral. And at a quantum critical point, what would happen is we have strong percolation such that the domain wall between a trivial chain and a Haldane chain strongly fluctuate and proliferate in space. Whenever there is a domain wall, we will have a free spin 1/2 degree of freedom. So at a quantum critical point, such kind of feature can be written.
All right, sorry, Yizhi,
Uh-huh.
is that a typo there? This actually should be a, sorry, it's a four component vector in the Weizmann-Witten term, right?
Yes.
So it shouldn't be O3 level 1 though.
Oh, okay. This is domain wall of theta.
Oh, domain
yeah, this
wall.
is what I will I will clarify it in just a minute.
Okay. Okay.
So the field theory is actually an O4 level 1 Weizmann-Witten term, where the first three components correspond to the spin rotation symmetry, and the fourth component correspond to different patterns where we have spin entangled within the side or between the side, or that correspond to the theta term, where theta is either 2 pi and 0. And the existence of this O4 Weizmann-Witten term actually reflects a fact that whenever we have a domain wall of theta, where theta jump from 0 to 2 pi or vice versa, it would capture, the domain wall of theta would capture a zero-dimensional O3 Weizmann-Witten term, which interpret a spin 1/2 degree of freedom. So does it answer your question?
Can I ask a possibly very silly question here? So you have domain walls between theta equals 0 and theta equals 2 pi. From the point of view of the low energy effective field theory, can I think of this as you secretly have some axion or something that allows domain walls to be dynamical in the O3 signal?
Yes, exactly.
Oh, okay. Thank you.
And at the quantum critical point, at two phases, theta have to be quantized, flow into quantized value, which is 0 or 2 pi. These are the stable fixed point of theta. And at a quantum critical point, the theta strongly fluctuate in a bulk, and such kind of fluctuation or domain wall of theta term carries a spin 1/2 degree of freedom. It's encoded in this O4 level 1 Weizmann-Witten theory at a quantum critical point. So from this simple and prominent example, what we learn is there are a large number of phase transition beyond the Ginzburg-Landau paradigm, like this Haldane chain toward the trivial chain phase transition. And what happened there at a quantum critical point is, in the Haldane chain, there is an H mode, carries a spin 1/2 degree of freedom. Once we drive the phase transition toward a quantum critical point, this H mode, which was previously localized in the boundary, now fluctuate into the bulk and dissolve into the bulk. And this H mode exists as a domain walk between the SPT pattern and trivial patterns. And because these two patterns has a domain walk, the quantum critical point has a new type of term that is encoded in terms of the O4 level 1 Weisman-Witten term, which would change the universality. So the topological information is actually encoded in the quantum critical point or proximity to the quantum critical region, and hence qualitatively change the phase transition theory. Okay, so after review this well-known example, we can go to a model I will focus on today. So what I will talk about today is a new type of topological phase transition, which connect two phases with the same pattern. And these two phases is a higher order topological insulator phase that I will discuss in just a moment toward a trivial Mott insulator phase. These two phases have the same symmetry pattern, but they have different topological invariant, which is characterized in terms of a quantized quadrupole moment. And in particular, this phase transition is elusive in the sense that first, it's a topological phase transition beyond the Ginzburg-Landau paradigm. And second, this phase transition is also beyond the renormalization group theory because the short wavelength physics or local fluctuation plays an extremely important role at a quantum critical point because of UV and IR mixing. Okay, so now let's begin with a model, what we call a high order topological insulator. So this is a 2D model on a square lattice where each side, this pink island, contains 4 spin 1/2 degree of freedom, or we can regard them as 4 hard-core boson degree of freedom on the same side. And the Hamiltonian is mainly dominant by a ring exchange term, which has a 4 spin interaction or 4 hard-core boson interaction with a ring exchange form between the 4 spin on each plaquet. And this ring exchange term would finally have a tendency to project the 4 spin or say 4 hard-core boson on each plaquet between the unit cell into a 4 spin maximal entangled state like this. And now let's look at the symmetry we have. So the symmetry we will keep throughout the phase transition is we need to have a time reversal symmetry for the spin. And in the meantime, we will have a new type of symmetry, which we call the subsystem U1 symmetry, such that if we take each row and each column, we will find the U1 charge of the hard-core boson, or say the SZ charge for the spin, is conserved on any row and any column. And that is why between the unit cell, we can only have a ring exchange term such that there is no way for you to hope a magnon between the sides, but we have to hope a pair of magnon, like particle hope pair, in a direction that is perpendicular to their orientation. And what happened to this Hamiltonian? So bulk, this ring exchange term project 4 spin in the bulk into a 4 spin entangled state in a plaquet. So the bulk charge degree of freedom is fully gapped. And at a boundary, if we have something like a smooth boundary here, there will be 2 free dangling spin live on the same side. And with any infinitesimal spin XY or Heisenberg interaction, these 2 spins would finally be paired up. And there's no free gapless degree of freedom at a smooth boundary. What is tricky is what would happen at a rough boundary. So if we have a corner, this corner would contain additional spin 1/2 degree of freedom, which cannot be gapped out if we have time reversal symmetry and a subsystem U1 symmetry. So this is what they called a higher order topological insulator, where the charge degree of freedom inside the bulk and the smooth boundary are fully gapped, but there exists a free spin 1/2 zero mode localized at the corner, which is protected by symmetry. And in particular, here, the spin 1/2 degree of freedom localized at the corner is protected by both the time reversal symmetry and subsystem U1 symmetry. So for time reversal symmetry, it has to be unbroken. Otherwise, we can always polarize the spin at a corner in the Z direction. In the meantime, the subsystem U1 symmetry is also important Without a subsystem U1 symmetry, in principle, we can either drive a phase transition, which only appears at a boundary without closing the bulk gap, to hybridize the two spins from the two corners and fully gap them out. Or without subsystem U1 symmetry, in principle, I can always decorate something like a 1D AKL T-chain at a boundary. And the additional zero mode will finally gap out the corner mode. In the presence of such kind of subsystem U1 symmetry, we will find the Magnon charge, or the charge U1 at this corner and the charge U1 at this corner belongs to different charge sector, because the charge on this row and this row have to be conserved. And hence, if we have subsystem U1 symmetry, there's no way for you to hybridize the two spins localized at a corner in a way, unless you unless you close the gap at the bulk. So this is something like a higher order topological insulator, which is protected by both the global time reversal symmetry and a subsystem U1 symmetry. So now we are convinced that this is a higher order topological insulator. And this actually belongs to a strongly interacting higher order topological insulator, because in free fermion theory or band theory, usually it is very hard to find a system which can manifest a subsystem U1 symmetry where charge on any row and column have to be conserved. And in order to convince this is a topological symmetry protect topological phase, we probably want to figure out a topological invariant which distinguishes such kind of higher order topological insulator with any other trivial insulator or trivial mod insulator. So the next step is, does such kind of high order topological phase have any topological invariant? There are different to deal with topological invariant in strongly interacting SPT phases. And one way we will show here is, we can show the topological invariant or figure out the topological invariant by looking into the topological response theory of the higher order topological insulator. And in particular, because here there's a subsystem U1 symmetry, we can gauge the U1 symmetry and look for the electromagnetic response after we gauge such kind of U1 symmetry for the higher order topological insulator. If there exists a topological electromagnetic response whose coefficient is quantized in the presence of symmetry, then this quantized coefficient should be a good fingerprint or signature to characterize the higher order topological insulator. So now let's gauge the subsystem U1 symmetry. So this subsystem U1 symmetry is a bit tricky and different from the usual U1 symmetry. For the usual system with the U1 symmetry, once we gauge it, then we just couple it with the usual U1 electromagnetic field. However, in this system, the charge is conserved on any row and any column. So what would happen is, in our Hamiltonian, any spin Magnon Hoping term or boson bilinear interaction between the unit cell is not allowed, because they break the subsystem symmetry. And the only allowed term varies of ring exchange term, which create a pair of a particle hole pair, a Magnon particle hole pair, which I call the dipole, and let it fluctuate in the transverse direction. So if we want to gauge such kind of subsystem U1 symmetry, the gauge potential we introduce should be a high rank gauge potential, which I will call AXY, and let that live in the center of the plaqué for each ring exchange term. And once we gauge the subsystem U1 symmetry, such high rank gauge potential should be minimal coupled with the ring exchange term. And actually in 2D, this is the only spatial component of the gauge potential. It has a special gauge transformation like this, where there are two spatial derivatives in front of smooth field. And in the meantime, we also have a time component, A0, which couple with the charge density. So once we gauge the subsystem U1 symmetry, we figure out there are two types of gauge potential we can write down. And if we only consider the leading order, the tadpole diagram, the lowest order term we can write down, which is gauge invariant, from this gauge transformation is this term, which I will call the quadrupolarization term. That's the leading order term in the topological diagram, which is gauge invariant. And the coefficient in the front is what I will call the quadrupole moment, which turns out to be a dimensionless constant. So now we know the leading order response is something like a quadrupolarization terms, and its coefficient is a quadrupole moment. But we are looking now is not something, it's not just a response theory. What we are looking at is a topological response theory. So our hope is we want to figure out whether this quadrupolarization response can have a quantized coefficient such that theta can only take some discrete value in the presence of symmetry constraint. So first, because this higher rank U1 gauge field is compact, it is not hard to argue that under a large gauge transformation of higher rank flux insertion, the theta is invariant under any 2 pi shift. So theta is 0 versus theta equal 2 pi are actually the same if the subsystem U1 symmetry is compact. And in the meantime, remember the system has a time reversal symmetry. And under time reversal symmetry, because time reversal symmetry act on the spin degree of freedom, and when it act on the SZ rotation, what would happen is A naught becomes minus A naught, and the spatial component AXY becomes minus AXY. So this quadrupolarization term, if we apply time reversal symmetry operator, the quadrupolarization term would acquire a minus sign. And since the ground state and the system is time reversal invariant, so the linear response.
Can I interrupt with a question?
Sure.
Yeah. So I think we might have discussed this before, but
yes.
I think it's just a terminology question. So your time reversal doesn't flip the sign of the time coordinate. Does it look more like a charge conjugation rather?
Yes.
Okay, thank you.
Since the system is time reversal invariant, what would happen is we can only take 2 discrete values, where theta is 0 and pi. And after a time reversal flip, theta becomes 0 or minus pi. And because theta has an ambiguity, or actually it is invariant under a 2 pi shift, so pi and minus pi are actually equivalent. So in the presence of time reversal symmetry and subsystem U1 symmetry, this quadrupolarization term has a quantized response.
Can I interrupt a little bit? So
yeah,
I also have the question about time reversal. So actually, since here time reversal A change sign, it's so A transform just like the ordinary electromagnetic field vector potential, and then in that case we know the electric field should be even on time reversal. But here, if you take A change sign but T does not change sign, it means electric field, which is a partial TA, should be odd on time reversal. So this time reversal seems a bit unnatural. Just suppose we take the convention from the ordinary electromagnetism.
True. So as Shuhan actually mentioned, the reason I called it time reversal is because previously it's more like a spin flipped. And in the hardcore boson language, it is more like a charge conjugation where particle becomes whole and whole becomes particle.
Okay. Yeah. Another thing I'd like to confirm with you is that, so now suppose we count the degree of freedom. It's like on every plaquette you have A, and on every side there's a constraint, and the side number equals to the plaquette number on the square lattice. So it means that overall speaking, there's no rest degree of freedom. So all the degree of freedom should be eliminated by the constraint. I mean, this is again very similar to the 1+1 dimension electromagnetic field. So should I say the only possible response theory is the topological theory? It's just like, yeah, I'm saying that. So just like the 1+1.
Yes. So you mean for the tadpole diagram, the only possible theory or only possible gauge invariant term is this term.
Yeah, you cannot generate, in principle, you cannot generate much other term because actually,
actually, you can have more spatial derivative in front of that.
I'm just wondering, like, how many, well, so whether A can have a propagating mode or not seems like all the degree of freedom has been eliminated by the constraint, because now the constraint equals to the number of degree of freedom.
Okay, good question. So first, actually, if you just want to write down a gauge invariant term in the tadpole order, in principle, if you add more spatial derivative in front of that, that is also allowed. But these additional terms would not give rise to any propagating mode for this A, because here we only have one spatial component of A. Yeah. So A actually does not have a dispersion.
Okay.
And this term is actually a boundary term. It's a pure boundary term.
Yes, yes.
If you have
also like
space-time.
Yeah. Okay. Cool. Yeah. Okay. Yeah. I think that's consistent with what I thought. Okay. Fine. Yeah.
So now we have a quantized quadrupole moment. And for the higher order topological phase, this corresponds to the case where theta equal pi, where for any trivial mod insulator without any corner mode or with only on-site entanglement, that corresponds to theta equals 0. And what does this quantized response tell us? So the saddle point of equation of this response tells us that there is a charge density localized at a defect where theta is changed at a corner. So if we plot a spatial configuration that in this corner, theta is pi, and outside that, it's the vacuum or any trivial mod insulator, what would happen is partial x, partial theta has a delta function at this corner. And this linear response, which came from the topological quadrupolarization, tells us once we have a corner, we will have a half charge, half SZ charge, which exactly correspond to a spin on degree of freedom or free spin 1/2 localized at a corner. Okay, so now I have introduced this new type of high order topological insulator, which has a quantized quadrupole moment, and that quantized quadrupole moment itself indicates if you have a corner where theta jumps from pi to 0, there should be a free spin 1/2 mode localized at a corner. And since the main focus of this talk is about phase transition, so now we will try to add some additional terms and try to drive the high order topological insulator toward a critical point. So the model I consider is still the same model, a square lattice with 4 spin per unit cell. And there are two types of interaction. One is the plaqué interaction we just introduced to engender a high order topological insulator. And the second type of interaction is any XY interaction which appear between the 4 spins within the unit cell. So because these are the interaction inside the unit cell, any XY interaction within the same pink island does not break any subsystem U1 symmetry, and it does not break time reversal symmetry as well. And for this model, which has an intrasite XY interaction versus intersite plaqué interaction, there are two limits, which is pretty clear. First, when plaqué interaction is extremely large, when lambda is large, then we go back to our previous higher order topological insulator model where it contains a protected corner mode. And if lambda is very small and the bound interaction, the XY type interaction within the unit cell dominate everything, then the 4 spins are projected into a spin entangled state within the same unit cell. So this is a trivial mod insulator where spins are just a pair inside the unit cell and there's no entanglement at all between different unit cells. And higher order topological insulator correspond to the fact that we have a quantized quadrupolarization with theta equal pi, and a trivial mod insulator correspond to the fact that theta equals 0. So what would happen if we continuously tune this lambda? And a numerical simulation, which is mainly implemented by Pullman's group at Technical University of Munich, shows that once we continuously tune this lambda, which is the ratio between the plaqué interaction and bond interaction, it turns out that there exists a quantum critical point, or actually second order phase transition, which connect the trivial Mott insulator phase and the higher order topological insulator phase. So this is a phase transition point which connect two phases with the same symmetry pattern. Both of them have the same time reversal symmetry and subsystem U1 symmetry, and they also do not break any lattice symmetry. However, they show distinct topological pattern because one carries a quantized quadrupole moment with theta equal pi, the other carries a quadrupole moment with theta equals 0. What happened at this critical point? How do we develop theory to characterize this phase transition point? So first, let's take a look at what would happen when that lambda is comparable. So if we begin with this trivial phase, where spin XY interaction within the unit cell dominate everything, then the spin are localized inside each unit cell. However, once the plaqué interaction grows larger, then the spins, or say the magnons, has a tendency to fluctuate between sites. However, because we only have ring exchange term due to subsystem symmetry constraint, what would happen is a single magnon cannot hold between the sites, but what would happen is two magnons, a particle hole pair, can fluctuate in the transverse direction. So once the plaqué interaction and bond interaction becomes comparable at a quantum critical point, what we can expect is it is not something like a magnon liquid where magnon is fluctuating. It's more like a dipole liquid where a pair of magnon is strongly fluctuate along the transverse direction.
Sorry, I have a quick question. So is this 2.5 spatial? So how do I see this transition point quickly? For example, by comparing the energy of bond and the plaqué, can I see this 2.5?
Actually, what we look at is the divergence of the correlation lengths. This is how we pinpoint the quantum critical point.
Is exact 2.5 or just approximately?
It's actually from the numerical data, it's 2.51, but I believe there's some finite size effect there, and it's pretty. I don't know what would happen at the thermodynamic limit, honestly. This is from numerical prop, not from theory.
Okay, thanks.
Let's think about a pictorial way to understand the quantum critical point. So at a quantum critical point, the ring exchange term and the on-site XY interaction are of the same strength. And that plaqué ring exchange term would favor a plaqué entangled state, which I will illustrate them as a red region with a quantized quadrupole moment pi, while the on-site XY interaction would favor something like a Mott phase pattern with only on-site entanglement, and that corresponds to the fact where the quadrupole moment theta is 0. And at the quantum critical point, these two type of patterns compete, and we can imagine the wave function is a superposition of all possible configurations with spatial separation where some of the region, the red region, correspond to theta equal pi, where everything is entangled in a plaqué pattern, while some of the white region correspond to the region where theta equals 0, where everything is entangled into an on-site singlet. And these domain walls, which spatially separate two distinct patterns, topological and trivial patterns, would proliferate and strongly fluctuate in space. And what happened to the domain wall? So this is a concrete illustration of the domain wall. Domain wall is actually a phase boundary, spatial phase boundary between the higher order topological pattern versus the trivial Mott pattern. And the smooth part of the domain wall does not carry any 0 mode. However, the rough part of the domain wall, which is what we call the corner, is nothing but a corner between a higher order topological phase versus the vacuum or trivial phase. And that actually contains a free spin 1/2 degree of freedom or spin on 0 mode. So once these domain wall patterns, which spatially separate higher order topological insulator pattern and trivial pattern fluctuate, what would happen on the domain wall is the smooth part of the domain wall is fully gapped. But at the rough part of the domain wall, the corner, there exists a free spin 1/2 mode. So again, at a quantum critical point, the previous corner mode, which is localized at a corner of the higher order topological insulator, now fluctuate into the bulk and dissolve into the bulk as they are dressed on the corner of the domain wall. And at one critical region, the domain wall does not have a fixed pattern. It strongly fluctuates, and there's resonance of flipping between one domain wall pattern versus another domain wall pattern in space-time. So what happens is we can imagine the domain wall flipping can be illustrated in a configuration like previously we have a domain wall of this pattern, and the domain wall can shrink a little bit from the left side. And once the domain wall shrink or fluctuate between distinct patterns, what would happen is the previous corner mode, two corner mode, which live here, now have a parallel jump. They're moving in a transverse direction to their orientation. So this is a more concrete illustration of the domain wall fluctuation. Once the domain wall slightly shrink to the right direction, what happens is it transport a pair of spin-on, which are the two corner mode, in the transverse direction. And on the lattice model, such kind of pair of spin-on transport along the transverse direction is something like a ring exchange term. Or another typical domain wall fluctuating pattern is previously we have this something like a rectangle domain wall, and the domain wall can shrink a little bit somewhere. And this corresponds to the fact that previously we have a spin-on mode here. And after that, this spin-on at this corner is annihilated and create three spin-ons at the other three corners. And again, in the lattice model, this corresponds to some ring exchange term, which annihilate spin-on here and create three spin-on at the three new corner. So once the domain wall is strongly fluctuating, the spin-on zero mode decorate at the corner mode is also fluctuating. However, because this spin-on zero mode only live at a corner, the spin-on fluctuation when they dissolve into the bulk have some Fracton dynamics. A single spin cannot fluctuate along any direction. What would happen is we only have a pair of spin, which is fluctuate in the transverse direction to their spatial separation. So if we want to write down some Gaussian type field theory to characterize this spin-on dynamics when they dissolve into the bulk, what would happen is there is no dx or dy theta term because a single particle cannot fluctuate. Instead, the leading order kinetic term is something like dx dy theta term, which implies a pair of spin separate along x would fluctuate along y direction, or if they're separate along y, they can fluctuate along x direction. So now it's a bit more clear. At a quantum critical point, the corner mode dissolve into the bulk with some elusive Fracton dynamics where a single charge cannot fluctuate and a pair of charge can only fluctuate along the transverse direction. And this critical point can be characterized by a critical dipole liquid because a single charge does not fluctuate. If we measure the correlation function of two magnon at a quantum critical point, they should decay faster than they should decay exponentially. Instead, since a pair of spin-on, something like a dipole, can fluctuate along the 1D stripe, if we measure the correlation function between two spin, I'll say actually two magnon, which are spatially separate along the x bond, and measure their correlation function along the transverse direction with large spatial separation, we will find this full spin correlation function, or the magnon dipole's correlation function, has a power law decay at a quantum critical point. And hence, such kind of quantum critical point can be imagined as a critical dipole theory. And this critical dipole theory comes from the fact that at a quantum critical point, the previous corner mode now dissolved into the bulk with Fracton dynamics.
I have a question about the parameter k. So in your upper equation, use the same k for those two terms.
Yes, yes.
Those two terms have different mass dimension.
True.
Right?
True. They have skin.
Okay, so you are suppressing some factor of lattice spacing?
Yes, actually, here first, I must keep the lattice spacing because of UV-IR mixing. Otherwise, there won't even be a gapped space. And actually, I keep the lattice spacing A as 1. and absorb here.
So there are various factors of A on this slide. Okay.
Yes, and I always keep the lattice spacing without changing it, which is actually pretty important, as we'll mention in just a few slides.
Thank you.
So the critical point has a critical correlation function between the dipole. And also, if we look into the static structure factor at a quantum critical region, we will find that the low energy part of the spectrum forms something like a bow type of the Fermi surface with zero energy mode extended along the kx and ky axis. And if this is the analytical result, and this is the numerical result obtained by Bibo and Pullman. And if we take out a slice from the momentum space, they do behave like a 1D relativistic boson, which came from the fact that a pair of spinon can fluctuate along the 1D stripe, just like 1D relativistic boson once we fix one momentum. So at a quantum critical point, the zero energy mode is not just localized as small momentum, it is extended along both x and y axes, and hence the specific heat will be pretty different at a quantum critical point. It should scale as T log n T because we have excessive number of zero energy mode on two axes. And in the meantime, at a quantum critical point, the ground state wave function has a very long range entanglement entropy, which scale as L log n L because of this Bose type of the Fermi surface with excessive number of zero energy mode along two axes. And finally, I'm about to finish. So let me talk about the most striking result of this critical point. So if we talk about critical point, we can look into the correlation function and look into the scaling dimension of different type of operator. And historically, we know the critical point, the scaling dimension should turn out to be very universal. It's only dependable to the spatial dimension locality and the symmetry, and only the long wavelength physics contribute to the quantum critical point. However, in this quantum critical point, if we measure the SZ correlation function, it has a power law decay, but it is fully anisotropic, does not fit into any of the well-known universality. And because it's anisotropic, so in some special direction, it seems to be power law, but in some diagonal direction, it seems to be more long-ranged. In addition, if we look into the Magnon correlation function in both temporal direction or spatial direction, they have short-range correlation function. However, if we look into a higher order spatial derivative of the Magnon operator, which is more like a dipole Magnon operator, it decays in a power law manner. This is very peculiar and counterintuitive, because from the renormalization group picture, it turns out that whenever we have a spatial derivative in front of an operator, by dimension counting, it should be less relevant. And also from the renormalization group picture, if we have additional spatial derivative in front of an operator, we're actually looking into some rough configuration of that operator. And a quantum critical point, the rough configuration should not play an important role, and we usually expect them to be less relevant. But here, they're even more relevant. What happened here? So what happened here is, because of the Fracton dynamics, or because of the subsystem symmetry such that a charge cannot fluctuate while a pair of charge can only fluctuate on the transverse direction, there exists a large number of zero energy modes or low energy mode, which came from the local fluctuation. Remember, when we look at a structure factor, it turns out that the zero energy mode is extended in both kx and ky axes. So even at very large momentum k, we can have a zero energy mode. If we do Fourier transform for these modes, that corresponds to a pattern where the field configuration is strongly fluctuate along one direction. So this mode actually corresponds to some short wavelength physics mode. However, this mode still survive in the low energy part of the spectrum. Actually, they live on this Bose type of the Fermi surface because we have two spatial derivatives in front of the theta term due to subsystem symmetry. So what happened at a quantum critical point is there exists a large, actually sub-extensive number of zero energy mode, which is contributed by short wavelength physics with strong fluctuation. So what happened at a quantum critical point is there is something what Shuhan and Nati called UV and IR mixing, such that the UV modes or high momentum modes with rough configuration finally enter and survive in a low energy part of the spectrum. So that is why we finally end up with a peculiar quantum phase transition, which first, it is beyond the Ginsburg-Landau paradigm because it is a phase transition, continuous phase transition, connect two phases with distinct, with the same symmetry pattern, but distinct logical features. And second, at a quantum critical point, what happened is the previous corner mode localized at higher order topological insulator now dissolve into the bulk, and they have Fracton dynamics. Because of these Fracton dynamics, at a quantum critical point, the low energy part of the spectrum at a critical region is dominated and contributed by a large number of short wavelength modes. So short wavelength physics plays an extremely important role at a quantum critical point. And that is why this picture is beyond renormalization. And the usual coarse grain sometimes could be illegal because whenever we are doing coarse grain, we're assuming that we are ignoring some type of short wavelength modes, which usually it is fine because they won't create singularity. However, here we have a large number of zero energy mode at finite momentum. So whenever we do coarse grain, we are actually ignoring some zero energy mode at both type of the Fermi surface, which should create additional singularity to the low energy behavior and hence change the correlation function qualitatively.
So can I ask a quick question? So, I mean, naively, can I just think of this that, if I do some kind of naive block spin coarse graining that doesn't play well with the subsystem symmetry, somehow you're losing some of the...
Yes, exactly. Because actually the charge on different rows and columns are independent. And once you are coarse graining them out, you are actually ignoring some subsystem symmetry.
Right. So there's no
cut off
expectation
some
that
of
this
the
RG should work because it's ignoring. Okay.
True. So I think I'm running out of time. And finally, as a take-home note, from this example, we can have an outlook which implies that there are a large number of new type of phase transition that is beyond renormalization. Today, we talk about a special type of topological phase transition, but we can expect there are a large number of spontaneous symmetry breaking phase transition, BKT-like transition, and order by disorder phase transition that does not fit into the renormalization paradigm. And the essence of this beyond renormalization group phase transition lies in the fact that there is a UV-IR mixing such that a short wavelength physics can survive, and a large number of short wavelength physics survive at low energy, and they can qualitatively change the low energy behavior at a quantum critical point. And thus, there will exist a large number of phenomena, which is pretty counterintuitive. For example, the critical exponent is now independent of space-time, and there can even be some emergent fractal dimension at a quantum critical point. The effective theory or the correlation function of an operator now depend on the UV cutoff, and we cannot do coarse grain arbitrarily. And sometimes the higher order operator turns out to be more relevant at a quantum critical point. And these higher operator are actually the essential operator which drives a phase transition. So finally, I'm running out of time, but thanks everyone's attention. And finally, I would like to acknowledge my collaborator. The topological invariant is explored by Taylor Hughes at UIUC and Fiona Berner at U Minnesota. And the numerical simulation of that phase transition is completed by Frank Pillman, a student at Technical University of Munich. Thank you.
Okay, great. Thanks for a really nice talk, Yizhi. So we have some time for questions. And actually, I have a very, very good question I want to ask. I mean, sort of maybe very general, but right. So you say that, you can't at least naively use this RG framework. I mean, does that mean everything is gone? I can't think about, there's no notion of RG fixed point, RG eigenvalue. I mean, what's the structure that remains?
For this example, it is there's still some new type of renormalization, which was probably explored by Chen Ke-Xu and also Masu Fisher, well, more than 10 years ago. And what happened is something like the Fermi surface, because once we do RG, we have to avoid touching additional zero energy mode. So what we do is we will fix one momentum or fix the spatial dimension of the dipoles, fix one lattice spacing along x direction and only renormalize along the y direction. So this would avoid additional zero energy mode. This is similar to the Fermi surface where for each patch, we only renormalize along the transverse direction. We won't renormalize along the parallel direction. Otherwise, you are including or excluding additional zero energy mode. But this is only for this example. There are additional examples where we have fractal symmetric symmetry conservation such that the Z2 symmetry is conserved on each fractal. And there, I don't find a reasonable way to do any coarse grain, honestly.
But is there still some notion of universality, or I mean, in those examples where you can't do coarse graining in any way?
Probably yes, but right now I don't find a reasonable way to do coarse grain. There are some interesting universality which shows that the scaling dimension is not just related with the spatial dimension, it's also related with the subsystem symmetry dimension of the many-body system.
Okay.
So can I comment on the RG part and probably maybe a little bit later to the last question. So so actually I think normally when we do RG, it means we are doing the energy and the momentum RG in the same time, because in ordinary field theory, low energy means low momentum. But here it's not the case anymore. Low energy means low momentum. We can still have a high momentum, but actually low energy. So it means that we are just doing an energy RG instead of momentum RG. It's yeah. So as Yizhi pointed out, it's pretty much the same spirit as like a Fermi surface RG. And also in terms of universality, actually the scaling dimension is no longer that universal anymore, but whether a correlation is power law or something different from power law, that actually may still be universal. So for example, you mentioned there's a costly Southeast transition, you know, something like that. So in those scenarios, actually, the scaling of the correlation length is no longer a power of the tuning parameter or something else. So the difference between power law and non-power law, that part is universal, but actually the scaling dimension, the actual power may not be that universal anymore. So we just have to redefine what is universal. I mean, what does universal mean?
I also have a related comment on this point. So in ordinary RG, high momentum means high energy. And therefore, when we write down the Wilsonian effective field theory Lagrangian, we can throw away the higher derivative terms because they will have negligible correction to the low energy modes. But precisely because of this UV-IR mixing in this class of models, we actually cannot throw away certain higher derivative terms. Like in your first line, I think actually it's only fair to add all those higher derivative terms that preserve the subsistence symmetry. So for example, we can have dx square dy theta quantity square. That preserves the U1 subsistence symmetry, but its correction to certain modes of this model is still significant, despite the fact that it comes with higher derivative. Thanks.
Yeah, actually, there is a similar question from the chat. Can you elaborate on the scaling fluctuation of high order multiple operator in your critical dipole liquid? Actually, this is a very important question. Also, Shuhan probably mentioned in his previous talk. So what happened here is higher order operator are more relevant. So this dipole liquid can be extended into a three-dimensional classical XY model with only Plaquet interaction on XY plane. And what happened there is a BKT type of phase transition. But if we look at the correlation function or the energy between two vortex, they will not proliferate. What happened to that Fracton type of BKT transition is a pair of vortex, which is something like vortex dipole, are more relevant than the vortex itself. And it is actually the vortex dipole proliferation which drives that phase transition between an order phase toward a liquid phase. And the reason for that is in usual renormalization group picture, because long wavelength physics survive at a low energy degree of freedom. So those rough configuration or higher order operators are actually less relevant and they do not have too many mixing with the low energy degree of freedom. But here, because short wavelength physics survive and contribute to the low energy behavior, those rough configuration or higher order operator actually have more resonance with the low energy part of the spectrum. And that is why they can be more relevant at the quantum critical.
Okay, looks like Alexei is raising his hand.
Yeah, I have a probably related question. So sorry if you've already addressed it actually, but how many higher derivative operators are there that are consistent with these symmetries? And the worry you would normally have, right, if some higher derivative operators are allowed, is that like you have an infinite number of them. So is there some finite number that are consistent with your subsystem symmetries?
Yes. So the leading order term, which is allowed by subsystem symmetry, is this dx dy term. And in principle, you can have some high order term like dx squared, dy squared terms or something like that. But this is the leading order term, which drives the kinetics of those dissolved corner mode.
But I think for certain modes, there's no sense that this is the leading term.
That's what I'm worried about. That's what I'm worried about.
But for generic plane wave modes, you are right that this is the leading term. But there are some other modes that receive corrections from infinitely many higher derivative terms that are compatible with the subsystem symmetry.
True, but
go ahead.
True, but adding these terms will not change the existence of this both branch at the axis. What will change it will slightly change the dispersion nearby, right?
So it will not change the qualitative scaling feature of the spectrum, but it will change the quantitative number of their energy.
I see.
So there's another question from Dominic.
Yeah, hi. So I wanted to ask again about this concept of UV-IR mixing. So just to be clear, you're only talking about mixing in terms of momentum space, not in terms of energy, right?
Yes.
And so would you, for example, say that a Fermi liquid also exhibits UV-IR mixing or not? True. Or is this totally different from what a Fermi liquid does?
Exactly. Actually, Fermi liquid is probably the first condensed matter system which contains UV-IR mixing. And that is why when we cross-grain or implement renormalization for Fermi patch, we have to renormalize along the transverse direction, like treated like 1D relativity.
Right, but a Fermi liquid, you can still think of it in terms of an effective theory that contains only long wavelength fluctuations. It's just that the fields are now labeled by like where you are on the Fermi surface, right? So in that sense, you recover an IR description. It just has this extra label for the fields. So is there something like that here?
Actually, I remember in your previous talk, you said that for the Fermi liquid, actually there is an emergent U1 symmetry, infinite number of U1 symmetry for each patch.
Right.
And for that, actually, then that's the same. Even it's emergent, then once we have emergent U1 symmetry, in principle, we more like a subsystem U1 symmetry, at least it's for each patch. Then we can have a large number of degree of freedom, a large number of low energy degree of freedom, which is pretty rough in real space. And for the Fermi surface, actually, you can do renormalization, but you have to do renormalization in the right way, because if you renormalize it along the parallel direction, then you again have to have mixture with additional zero energy mode. And actually for Fermi surface, it is the case that if you fix the filling of the system, but enlarge the system size, you will find such kind of UVI mixing because you are introducing new and a large number of zero energy mode at the Fermi surface.
Thanks.
Chong has a question.
Yeah, hi Yizhi. So you, just to clarify, you mentioned there's a more complicated example with fractal subsystem symmetries. Could you elaborate on that? In particular, do you have a continuous transition there?
Yes, actually, it's actually from Monte Carlo study. It's actually the Newman-Moore model where on the triangular lattice, we only have 3 spin interaction on the downward triangle in the presence of external transverse field. And for that model, the Z2 charge is not conserved, but the Z2 charge is conserved on each fractal. If you take out a large Sierpinski triangle and count the Z2 charge inside that Sierpinski triangle, that charge number is conserved. And actually, if you tune the transverse field, there is a phase transition between the spontaneous fractal symmetry breaking phase, Z2 symmetry breaking phase, versus the paramagnetic phase. And there at a quantum critical point, if you measure the XX correlator, the energy density correlator, what you'll find is the scaling dimension is not related with the space-time dimension, albeit this is a 2D local lattice model. The scaling dimension of the operator is ln 3 over ln 2, which is exactly the spatial dimension of the 2D Sierpinski triangle. This is one of the example I know.
I see. Thanks.
Are there any further questions?
Can I ask another one?
Sure.
So suppose you have a higher order TI that's protected just by the point group symmetry, not by the subsystem symmetry. Does any of its physics survive?
No, they will not survive, because what would happen for this theory is once you have this term, but if you only have C4 symmetry but break subsystem U1, then a single boson can hold. So actually partial X theta and partial Y theta would appear, and theta correspond to the magnon. And what would happen is if you have such kind of subsystem symmetry breaking, and it would enlarge that critical point into something like a superfluid phase, because the single magnon can fluctuate, and once they fluctuate in 2D, they have a tendency to condense like a superfluid phase. Actually, in previous our work with Pullman, we just break it to subsystem symmetry to U1 symmetry and maintain the C4, also the lattice crystalline symmetry. And what would happen is there's a higher order TI phase, there's a trivial phase, and in between there's an intermediate phase, which is something like the superfluid phase or that XY phase.
Okay. Are there any final questions before we conclude? Okay, if not, let's thank the speaker again. First time, I guess. And so I just want to, before we close for today, I just want to remind people that Dominic Elsa is going to be giving a talk at 3 p.m. Pacific time today. So that's 6 p.m. Eastern. So tune in for that. And hopefully see a bunch of you then.